Okay, let's start this key. This is the key for the identities, chapter 3 of the Długopolski Trigonometry edition 3 book. 3.1, starting off, use identities to find the exact value of the function for the given value. We're given sine of alpha equals 3/4, and alpha is in quadrant 2, and we're asked to find tangent alpha. Using identities, this book suggests that we go through the Pythagorean identities. This is what it would look like. Starting off, knowing that sine squared alpha plus cosine squared alpha equals 1, we can solve for cosine and end up with cosine alpha equals plus or minus square root 1 minus sine squared alpha. Now, this plus or minus is because we had to take square root to solve for cosine. But what quadrant this angle is in tells us which one we're going to be. So quadrant 2, I know that all sine, cosine, tangent are positive in quadrant 1. Sine is positive in quadrant 2. Tangent is positive in quadrant 3. And cosine is positive in quadrant 4. This you may know as all students take calculus. So, in quadrant 2, cosine is not positive, it's negative. Only sine is positive. So sine is positive, cosine and tangent will be negative. So we know that we're going to be working with a negative. Now let's continue on. Cosine alpha is therefore negative square root 1 minus. Now sine alpha is 3/4. It's squared. Simplify that. That is negative square root 1 minus 9/16, which is negative square root 7/16, doing a little fraction work. This reduces to negative square root 7 on top and 4 on bottom. So that's cosine. We have cosine now, but we're trying for tangent. We can now use our another fundamental identity. Tangent alpha is sine alpha over cosine alpha. Sine alpha was given as 3/4. We know this is positive in quadrant 2. Cosine of alpha is negative square root 7/4. We know that was negative in quadrant 2. And we reduce this and we end up, let's see, we could put the negative out in front. We have 3/4. We invert and multiply and get 4 over square root 7. These 4's cancel, giving us negative 3 over square root 7. This is tangent. Now this might not be your final answer, but it is in some books. Other books require you to rationalize the denominator. So rationalizing the denominator would be multiply by square root of 7 over square root of 7, and thereby get your final answer of negative 3 square root 7 over 7. That's what this book likes. Okay, great. There's tangent. This is using identities. Now, personally, I don't think this way is the nicest way to do this, so I'd like to show you one other technique. Okay, so we know sine alpha was 3/4, and we're in quadrant 2. So I can create a quadrant 2 angle and represent it as a triangle like this. Alpha is the angle whose sine is 3/4. Now sine is opposite, so 3 would go opposite, and hypotenuse, 4 would go hypotenuse. So when in terms of alpha, opposite is going to be 3, hypotenuse is going to be 4, adjacent would be here, and that's the piece that we're missing. But we know Pythagorean theorem, which is a squared plus b squared equals c squared. Plugging in 3 for a or b doesn't matter. We'd get 9 plus b squared equals 16. That is b squared equals 7, and b is plus or minus square root 7. Same value we had before with the identities. Now the plus or minus. This comes from the step right here, square root. But which one do we have? Well, here we just think about the actual quadrant that we're in. From the origin, up is positive, down is negative, right is positive, and left is negative. So we're going left square root 7. So we end up with negative square root 7. And then we're going up 3, so that's positive 3. And the hypotenuse is always positive. Okay, now that we have our triangle representing sine alpha equals 3/4 in quadrant 2, we look for tangent alpha. And in terms of a triangle, tangent is opposite over adjacent. Opposite would be 3, adjacent would be negative square root 7. And we could either have that or we could rationalize as just demonstrated already and get our answer that way. So from alpha, opposite, adjacent, 3 over square root negative 7. Sorry, negative square root 7. So I think this is a faster way to go. You still do the Pythagorean theorem, but it's the direct one rather than the identity. So, but you get to choose. We did use an identity, fundamental identity, tangent alpha equals opposite over adjacent. So I would consider we followed the instructions, although that's not what the book asks you to do in this case. That's fine by me. There's our answer. Okay, great. Moving on. We have simplify the expression, cotangent x secant x sine x. This is just a matter of knowing our identities. So cotangent x is cosine x over sine x times secant x is 1 over cosine x times sine x. I'm going to put that over 1, doesn't matter. But what we notice is cosine over cosine is 1, that's a form of 1. Sine over sine is a form of 1. So everything is 1s here. The answer is 1. That's that. All right, number 3. 1 over cotangent squared x plus secant x cosine x. This is another simplify the expression. So we start off with knowing that 1 over cotangent x is tangent x. So 1 over cotangent squared x is tangent squared x. That's easier to work with, in my opinion. No more fraction. Secant x is 1 over cosine x times cosine x. Okay. What we have is cosine over cosine is a form of 1. Now don't think they cancel and there's nothing left. They cancel to 1, so we have tangent squared x plus 1. Okay, and tangent squared x plus 1 is secant squared x. Now that identity comes from the fundamental Pythagorean identity. Sine squared x plus cosine squared x equals 1. If we divide, let's see, we want a tangent. So if I divide by cosine squared x, so I can make my tangent, of course I have to do that everywhere. This results in tangent squared x plus 1 equals secant squared x. And that's the final identity we used. Great. All right, number 4, we have another simplify the expression. I don't see any obvious identities to work with yet, except for maybe sine squared, that's equal to 1 minus cosine squared. But I do notice cosine is in both terms. So that's a greatest common factor. So I can factor out cosine x, leaving me with 1 minus sine squared x. Sometimes the trigonometry is made difficult by the fact that it's simple algebra in the background, like this factoring out cosine x. Recall that if you factor, you're dividing, so if to check you'd multiply these back out. If you were to multiply those out, you see you get your cosine x times 1, that's cosine x minus cosine x sine squared x. All right, now we have 1 minus sine squared x. That is cosine squared x. So we have cosine x times cosine squared x. And this, like x times x squared is x cubed, Cosine x times cosine squared x is cosine cubed x. Recall that this is just a shorthand for cosine x cubed. Alright, 1 minus sine squared x. If we have sine squared x plus cosine squared x equals 1, and this is the one that I have memorized, if I wanted to get cosine, for example, if I subtract sine squared x, I get cosine squared x equals 1 minus sine squared x. That's the identity we used in this problem. Alright, great. Determine whether the function is odd, even, or neither. Alright. Now as far as odd functions, as far as odd functions go, odd, we have sine. Sine of negative x equals minus sine of x. Because sine is odd, cosecant is also odd. For an odd function, you can pull out the negative. Tangent is also odd. And therefore, cotangent is also odd. For the even functions, we have cosine. Cosine of negative x is the same as cosine x. You can disappear the negative. It doesn't factor out, it disappears. And along with cosine, 1 over that will still be the true. So secant negative x equals negative secant x. These are your odd and even trig functions, the basic 6. So what you have to do is you have to work out f of negative x and find out what you get. Do you get negative f of x, or do you just get f of x? Is it odd or even? So f of negative x on our problem would be cosine of negative x, secant, secant, cosecant of negative x. Now what I'm doing here, all I'm doing is going back up to my function, and I'm replacing x with negative x. Alright, now this first one, cosine, is even, and so that just reduces to cosine x. Secant is odd, so that one, I'm going to use a parenthesis, you can pull the negative out. So we can pull a full negative out. Now, our original function was cosine x, cosecant x. We now have negative cosine x, cosecant x. So notice the function, it's almost the same, except for the negative. So we actually have this is equal to negative f of x. Alright, now if we have f of negative x equals negative f of x, that is odd. So what we have for this problem is odd. Odd because f of negative x equals negative f of x. Done. Great. All right, this problem is also one with the odd and even information in it. So from the list in the previous problem, we know cosine is even, so we can replace cosine negative x with just cosine x. But tangent is odd, so we can replace that with negative tangent x, then minus sine x. Okay, so this first fraction, let me write it a little bit different. Not any different as far as it's still equivalent, but 1 over tangent x is cotangent x. And cotangent is cosine over sine, so we have minus cosine x times cosine x over sine x minus sine x. Now I see fractions, so I'm going to work on the right one, multiply by sine x over sine x, so that I can get a common denominator. Just trying to simplify, and when you have two fractions, usually the simplification means combine those fractions together. Alright, we now have minus, oops, let's try a different color. That erase doesn't work well, there we go. Minus cosine squared x minus sine squared x all over sine x. On the top, if I factor out of the negative, I get cosine squared x plus sine squared x. Still over sine x. Well, that's the fundamental Pythagorean identity. Sine squared plus cosine squared equals 1. So this equals negative 1 over sine x, which we can then go to cosecant x. Negative cosecant x. Final answer. This completes the review for section 3.1.